Welcome. Today, we're going to unlock one of the most beautiful and powerful tools in all of mathematics. So, picture this. You're asked to calculate 1 plus x to the 100th power. How would you even start? Trying to multiply that out by hand, yeah, that sounds like a total nightmare. But what if I told you a formula, discovered way back in the 17th century, makes this whole problem completely manageable? And that's where this incredible tool comes in. It was discovered by Isaac Newton, and it's called the Binomial Theorem. It reveals a stunning hidden pattern in numbers. Today, we're going to see exactly how this magic works. All right, so let's dive right in. Before we can tackle the big, fancy formula, we've got to start with the absolute basics, its fundamental building block. It's a simple idea, really. The word binomial, well, bi means two and nomial means term. So a binomial is just any old expression with two parts being added together, like the classic a plus b. Now, you probably remember this guy from your school algebra days, right? But what happens when that power gets bigger? What if we go from 2 to 3 to 4 or even higher? Okay, so let's see how this thing grows. We're going to expand a few more of these, and I want you to keep a close eye on something. There's a pattern hiding in here. So here we go. Expansions for powers of 2, 3, and 4. Now, notice a couple of things. The powers of A go down, while the powers of B go up. That's kind of neat. But the really interesting part? It's those numbers out in front, the coefficients. See that? We get 1, 2, 1, then 1, 3, 3, 1, and 1, 4, 6, 4, 1. So what if we just get rid of the letters for a second and only look at those coefficients? A really cool structure starts to pop out. Can you see it yet? Yeah, that beautiful, perfectly symmetrical pattern isn't random at all. It actually has a super famous name, and the rule to build it is, well, it's surprisingly simple. And this is Pascal's triangle. The way it works is just so elegant. See how each number is just the sum of the two numbers right above it? That's 6 in the bottom row. It comes from the 3 plus 3 above it. The 4? That's from the 1 and the 3. It's amazing. This simple triangle literally gives us all the coefficients we need for our binomials. Now, what's really wild is that this triangle wasn't new. Mathematicians in Persia, China, and Europe had known about it for centuries. But here's the problem. If you wanted the 100th row, you had to calculate all 99 rows before it. It was Newton who came along and basically created a master key, a way to jump straight to any row you want. Okay, so let's check out this master key. This is the formula, the engine, that lets us calculate any expansion we want without having to draw out a giant triangle. All right, there it is. And I know, it might look a little intimidating with all those symbols, but honestly, it's just a super compact way of describing that pattern we just saw. That big sigma symbol, that's just a Greek sigma, and in math, it's just a shortcut for, hey, add up all these things. The most important new part here is that little symbol in the parentheses, the nk. That little symbol, that is the heart of the whole thing. It's called the binomial coefficient, and it answers a pretty simple question. How many different ways can I choose k things from a group of n things? The formula to figure it out uses factorials, the exclamation mark, where you just multiply a number by every whole number below it. This is the magic that lets us find any number in Pascal's triangle without building the whole thing. And look how powerful this is. Let's try to expand x plus 1 cubed. We just plug n equals 3 into our binomial coefficient formula a few times, and what do we get? We get 1, 3, 3, and 1. The exact same numbers from the third row of Pascal's triangle. No fuss, no muss. Perfect. Okay, so you might be thinking, that's a pretty cool math trick, but who cares? Why does this actually matter? Well, it turns out its applications go way, way beyond just crunching algebra problems. This theorem is actually the foundation of a whole field called combinatorics, which is basically the art of counting. It's also the absolute backbone of probability theory, showing up in things like the binomial distribution, which you'd use to model, say, the odds of getting heads in a series of coin flips. And on top of that, it's crucial in statistics, physics, and even engineering. But this is where Newton's true genius just shines. The move that literally changed the course of mathematics was when he took this idea one giant leap further than anyone had ever imagined. He basically asked, what if the power, n, isn't a nice, neat whole number? What if it's a fraction, like 1/2? Or what if it's a negative number? And in this incredible moment of insight, he discovered the formula still works. But with a crazy twist. Instead of the expansion stopping after a few terms, it becomes an infinite series. It just keeps going forever, with each new term getting smaller and smaller, homing in on the exact answer. I mean, this was a complete game changer. By creating these infinite series, Newton essentially built a bridge between the tidy, predictable world of algebra and the flowing, continuous world of curves and motion. This idea became a cornerstone for developing calculus and the entire field we now call mathematical analysis. So you see, the binomial theorem is just this perfect example of the magic of math. You start with a simple question: how do you expand a plus b to some power? And it unlocks this deep, beautiful structure that connects totally different fields: algebra, counting, probability, and even the infinite world of calculus. So, the next time you see that simple expression, a plus b raised to the power of n, maybe you'll remember it's not just some boring algebra problem. Behind it, there's a hidden universe of mathematical patterns, a secret code that connects everything, a code that Isaac Newton helped us all to finally understand.